Hello everybody, welcome to Shaders Monthly. Today we talk about low discrepancy sequences and their application in computer graphics. In particular, we are going to implement the Halton sequence in GLSL. As an application example, we will use the Halton sequence to improve the image-based lighting approach that we implemented in the last 2 episodes. Let's start with a motivating example. Each of the 3 squares on this slide represent a continuous 2D domain. We are now generating 2D sample locations. Each sample location is represented by a small black dot. On the left you see the result of random sampling. In the middle is the result of the Halton low discrepancy sequence. And on the right the result of looping row by row over a regular grid. Random sampling is what we have used so far for image-based lighting when solving the integral of the rendering equation using Monte Carlo integration. However, when we look at the sample locations here, we notice that the samples are not evenly distributed. On the one hand, we have some gaps, which means that these areas do not contribute to the solution. And on the other hand, we have clumps, which means that these areas contribute more to the solution. This typically increases the noise in the output. Of course, if we continue to sample, this would all average out because we are using a uniform distribution. But for a relatively small number of samples, random sampling may not be the best approach. Let's look at the approach on the right. Here we are taking samples on a fixed grid. This is perfect in terms of evenly distributed samples. Each sample has the same distance to its neighbor. The downside is that such a regular sampling pattern can produce aliasing. This means that high frequencies in the input produce errors in the output. The regular sampling grid generates aliasing artifacts in the output with regular patterns that are visually very noticeable. In summary, the left approach is bad because of the noise, the right approach is bad because of aliasing. So let's use something in between as a compromise. This brings us to the topic of low discrepancy sequences. Here in the middle, we see the result of the Halton low discrepancy sequence. The Halton sequence produces samples that are to some extent evenly distributed. This means no gaps or clumps. On the other hand, the sample locations also show some irregularity. Okay, so how do we generate the Halton sequence? The Halton sequence is a function of an input index n and can produce an output vector in multiple dimensions. For each dimension, we evaluate the function hb of n, where hb of n is computed by mirroring the numerical value of n to the base b at the decimal point. In the following slides, we will look at some examples. Each dimension uses a different base, and these bases are prime numbers. For example, 2, 3, 5, 7, 11, 13, 17, 19, and so on. The generated samples have a uniform distribution. A Halton sequence of arbitrary length is possible, which means the index n starts at 1 and can go up to some large integer value. The figure here shows sample positions of the 2D Halton sequence. The x dimension uses h of n to the base 2, and the y dimension uses h of n to the base 3. Here we see how h2 of n is computed. Before we look into this, let's review what we mean when we write down a number from the decimal system in our everyday lives. We use the positional notation for our numbers. This means that the value of the digit, 0 to 9, is multiplied by a factor that depends on the position of the digit within the sequence. For example, when we write down the decimal number 9553.82, this digit here is multiplied by 10 to the power of 0, so the factor is 1. The next by 10 to the power of 1, which is 10. 10 to the power of 2, which is 100. 10 to the power of 3, which is 1000. After the decimal point, we have 10 to the power of minus 1, which is 1/10. 10 to the power of minus 2, which is 100th, and so on. When we use binary encoding, we have a base of 2. This means we have only 2 digits, 0 and 1. When we write down a binary number, we also use the positional notation. For example, the binary number 1110.010. This digit is multiplied by 2 to the power of 0, so the factor is 1. 2 to the power of 1, which is 2. 2 to the power of 2, which is 4. 8, 16, 32, 64, and so on. After the decimal point, we have 2 to the power of minus 1, which is 1/2. 2 to the power of minus 2, which is 1/4. 2 to the power of minus 3, which is 1/8, and so on. Now let's look at this table where we compute h2 of n. Here we have the index n as a decimal number. In the next column we write down the index n in the base 2 system, so as a binary number. For example, index 6 equals 0 times 1 plus 1 times 2 plus 1 times 4. Next we mirror the binary number at the decimal point. So we get 0.011. 011. The value of the mirrored binary number is 0/2 plus 1/4 plus 1/8, which is equal to 3/8. h2 of n equals 1 gives 1/2. h2 of 2 gives 1/4. h2 of 3 gives 3/4. 1/8, 5/8, 3/8, 7/8. We see that the resulting sampling positions are all in the range from 0 to 1. Note how nicely the samples cover increasingly finer intervals. The first sample is in the middle at 0.5. After 3 samples we have covered all the quarter positions. After 7 samples we cover all the multiples of 1/8. And this would continue, multiples of 1/16, multiples of 1/32, and so on. For the next dimension, h3 of n, we can do exactly the same, but now with a base of 3. This means we have 3 digits, 0, 1, and 2. For example, 12102.022. The digit to the left of the decimal point has a factor of 1, then 3, 9, 27, 81, and so on. After the decimal point we have 1/3, 1/9, 1/27, and so on. For example, the index 7 equals 1 times 1 plus 2 times 3 when encoded in the base 3 system. Again, we mirror at the decimal point. 2,1 becomes 0.12, which is 1/3 plus 2/9 and is equal to 5/9. When we look at the resulting sampling positions, they are again in the range from 0 to 1. First we cover the multiples of 1/3, then multiples of 1/9. And this would continue, multiples of 1/27, multiple of 1/81, and so on. Now, when we look at this result in one dimension, the advantage of the Halton sequence is not clear. Yes, we messed with the order somehow, but in the end, the selected sampling positions are exactly the same as for a regular grid. However, we get a different result when we look at multiple dimensions. Here we see the 2D Halton sequence. We take the first sample. h2 of n equals 1 gives us 1/2 in the x dimension, and h3 of 1 gives us 1/3 in the y dimension. In the x dimension, the next sample will increase the grid to multiples of quarters. And in the y dimension, we still have the 2/3 position unused. Okay, now we go to multiples of 1/9 in the y direction, and so on. The grid gets finer and finer. When n equals 26, we have covered all multiples of 1/27 in the y direction. However, you see here in 2D that not all 2D grid positions are covered with sampling points. True, every sampling point is on the grid, so there is some regularity, but the grid positions are sparsely populated and there is no obvious pattern. To implement the Halton sequence in GLSL, let's try to find an algorithmic solution. To this end, we look again at the Halton sequence for a base of 3. To compute h3 of n, we can iterate over the digits after the decimal point. Let's look at the first digit here. Its weighting factor is 1/3. There is a regularity in the corresponding nominator. 1, 2, 0, 1, 2, 012, 012, and so on. We can compute the value of the nominator by dividing the index n by the base, which is 3 here, and using the remainder. 1 divided by 3 is 0, and the remainder is 1. 2 divided by 3 is 0, remainder 2. 3 divided by 3 is 1, remainder 0. 4 divided by 3 is 1, remainder 1, and so on. If we compare the remainder with the nominator here, we see that this is exactly the solution that we are looking for. As in most programming languages, in GLSL we can compute the remainder using the modulus operator. Okay, we are finished with the first digit after the decimal point. Let's look into the second one. For n equals 1 or 2, we don't have a contribution here, and we are already finished after the first digit. In the algorithm, we can see that we are finished if the integer division by the base returns 0. See here, it's 0, and so we are ready. Otherwise, for the second digit, we have to move from a weighting factor of 1/3 to a factor of 1/9. This can be achieved by dividing 1/3 by the base 3, which gives us 1/9. Let's write down the result of the integer division from the first digit again. 1 divided by 3 is 0, 2 divided by 3 is 0, 3 divided by 3 is 1, 4 divided by 3 is 1, 5 divided by 3 is 1, 6 divided by 3 is 2, 2, 2, 3, 3, 3. Again we perform the division by the base, which is 3 here. 1 divided by 3 is 0, remainder 1. Same here, same here. 2 divided by 3 is 0, remainder 2. Same here. 3 divided by 3 is 1, remainder 0. Same here. We see that the remainder gives us the nominator for our digit factor of 1/9. 1, 1, 1, 2, 2, 2, 0, 0, 0, 1, 1, 1, and so on. Now we are finished with the second digit and continue with the third digit. Again by dividing by the base. 1/9 divided by 3 gives 1/27. For those n's where the integer division by the base is 0, we are done. Okay, let's implement this algorithm in GLSL. We use the GSN Composer at gsn-lib.org as a shader editor. The GSN Composer is a web-based tool that I created especially for teaching shader programming. But you can use any other shader editor as well. We are writing pure OpenGL GLSL code which you can use everywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. The implementation is based on our example from episode number 11, in which we performed image-based lighting by computing a pre-filtered environment map. Click Project and type in the project name Shaders Monthly 11 and click Open Existing. Then open the graph Prefilter Specular and press play in the time control panel. Let's use a crop node to crop out a region in the pre-filtered environment map that exhibits some sampling noise. We show the pre-filtered environment map and its detail magnification on the right side of the screen. There is some obvious noise here in the dark region. We select the shader node and click the Edit Code button. We add a function to compute the Halton sequence in the fragment shader. Float Halton, uint base, uint index. Float result equals 0. Return result. Let's add a variable that holds the weight for each digit after the decimal point. Float digit weight equals 1. For the first digit after the decimal point, this variable should be 1 divided by the base. Digit weight equals digit weight divided by float base. For example, for a base of 3, this weight would be 1/3. Next, we need to compute the nominator. We use the integer modulo operator %. uint nominator equals index % base. Compute the remainder with the modulo operation. Next, we multiply the nominator and the digit weight and add the product to the result. Result plus equal float nominator times digit weight. To prepare the index for the next digit, we need to perform an integer division by the base. Index equals index divided by base. If this reduced index variable is 0, we are done. Otherwise, we need to continue. So we put a while loop here. While index larger than 0, closing brackets. If this while loop is entered for the next digit, we see here that digit weight is updated. For a base of 3, the digit weight was 1/3 in the first iteration and is now divided by 3 again in the second iteration, and we get a digit weight of 1/9. The reduced index variable is used to compute the nominator again. We add the product of the nominator and the weight to the result. And so on and so on. At each iteration of the loop, the index variable is reduced by the integer division with the base, until at some point the reduced index is 0 and we have completed our computation. Consequently, the number of iterations of this loop depends on the number of digits that we have to process. The larger the index gets, the more digits it has. But fortunately, the number of digits only grows logarithmically. The number of digits equals floor log b of n plus 1. Now here in the sampling loop, we replace the random number generator with our Halton sequence. Vec2 random equals vec2 Halton 2 of n, Halton 3 of n. Furthermore, we should make sure that the index n now should start at 1, not 0. Apply code, recompute. Okay, yes, we can observe an effect. Again, this is a result of random sampling. This is the Halton sequence. The noise is significantly reduced. Let's change the input to a more difficult example with small bright light sources. This is the result of the random sampling. This is the result of the Halton sequence. Again, the noise is reduced, but we get strong aliasing instead. At the location of the bright light sources, the incoming radiance changes quickly, so there are high frequencies in the input, and these produce the aliasing artifacts in our output. So there is no free lunch here. If we want to get rid of these aliasing artifacts, we have to increase the sampling number and apply a low pass filter to the input by selecting a higher bitmap level. The other option would be not to perform importance sampling for the BRDF of the material, as it is currently done, but perform importance sampling for the incoming radiance. But that is another topic. Now, performance-wise, computing the Halton sequence in the shader is not perfect. As we have already discussed, the while loop has to perform log b of n plus 1 iterations. If the total number of samples is known in advance, we can use the Hammersley sequence instead. On the left side, we see the Halton sequence, and on the right side, the Hammersley sequence in 2 dimensions. The sampling points of the Hammersley sequence have a slightly more regular characteristic. The construction of the Hammersley sequence is very similar to the Halton sequence, except that the first dimension is simply computed by dividing n by capital N, where capital N is the total number of samples. So everything is shifted by 1 dimension. For the second dimension we use H2, and for the third dimension we use H3, and so on. Now, there is a fast implementation of computing H2 without using a loop. This can be achieved by rearranging the bits in a 32-bit unsigned integer. However, this only works for H2. This means that the first 2 dimensions of the Hammersley sequence can be computed very fast. I will copy the code of the 2D Hammersley sequence into the shader, such that you can experiment with it. This is a reference to the source. vec2random equals Hammersley n capital N. The result is very similar. Okay, that's it for today. If you have any questions, use the comments or get in contact with me. As always, if you prefer C++ or Java source code, this can be found in the video description. See you in the next episode of Shaders Monthly.